Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. My guest today is an interesting person. Todd Adams. He's a professor in the Department of Physics at Florida State University. We're going to be talking about the Large Hadron Collider and discoveries coming from it, and what's the future for this high-energy physics. He also works in the CMS experiment at CERN, which is all a part of this, and again, we'll go into it. So, Todd, thanks for coming. How are you doing?
I'm doing well. How are you doing?
Good, good. So in a way that the layperson can start to approach this, what are you studying? What is the Large Hadron Collider doing? And again, what's your work about?
So the Large Hadron Collider is probably the world's largest scientific experiment. So it's a particle accelerator that is built underground outside of Geneva, Switzerland. It's about 17 miles in circumference. And it accelerates protons going one way around a ring and protons going around the other way around the ring, and at several points brings those together to collide in the highest energy collisions that we have in a laboratory available. So we're studying those proton-proton collisions, and we're looking for what happens when you collide these particles. There's quite a bit we can learn from it.
What speeds are they going? Are you getting relativistic effects? Are you approaching the speed of light?
Yes, we are very close to the speed of light. It's 99.99, and I don't remember how many % the speed of light. So we are highly relativistic.
Yeah, I've heard there's a big difference in effects, that minute changes in speed as you approach the speed of light. Is that true? And what kind of effects would you see, and on what scales?
So as you approach the speed of light, it gets harder and harder to accelerate a particle to go to higher velocity. So the same amount of oomph that you give to a particle when it's moving slow will increase the speed a certain amount, but if you do that same amount of push later on, it'll increase the speed less. And this is due to relativity, and it comes about from a couple of consequences. The primary one, in my opinion, is that you can't go faster than the speed of light. No massive particle can go faster than the speed of light, and that's a consequence of this. As we get closer to the speed of light, it gets harder and harder to accelerate something to the speed of light, such that eventually it'd take an infinite amount of force in order to accelerate a massive particle to the speed of light. So.
But do you notice different effects if you're 99% of it versus 99.9% versus 2 nines or 3 nines, or are there differences?
It gets harder and harder, but it's the general effect is the same. So that's in order to get the particles up to the speeds that we are accelerating them to. It's actually a series of accelerators that do it. So there's a linear accelerator that then sends the particles into a small ring, that sends it into a bigger ring, that sends it into a bigger ring, that sends it into the Large Hadron Collider. So we start off with particles at rest. It's just protons are just a hydrogen atom without the electron around the outside of it. So they're real easy to get, but getting them up to the speeds that we need takes some effort. Once we do, we fill the Large Hadron Collider with beams of protons, and we run those, just keep them going around in a circle at constant speed for hours, sometimes up to a day of time.
Is there does anything happen to protons just accelerating them and continually accelerating them, or keeping them at a certain speed? Or do they're invariant, they don't change?
They don't change, but the higher the energy when you collide them, the finer the scale of things you can observe inside the proton, for example. So by having them go very fast, they have a lot of energy. at least a lot of energy in my world of particle physics. Compared to the real world, it's still a small amount of energy because the proton's pretty small. But by the higher the energy that you collide them with, the smaller scale of the inside of what's inside the proton that you study. So the proton is not a elementary particle. It has known structure to it. But what you see actually depends on how you're probing it. Sometimes it looks, if you're at very low energy, the proton looks like it's just a one particle there. And as you go to higher, you start to see the quarks inside of the proton. And if you go to higher energies, you get to see that there's gluons in there, and there are quark-antiquark pairs being created out of vacuum. And normally, if you're looking at it at low energy, you're not seeing those effects. But if you're looking at it at high energy, you can see them. So that's one of the reasons why we go to such high energies and high velocities, and we've built such a big accelerator. The other is just so you have that energy there for the collision. And one of the main things that we're trying to do is create new particles that weren't there in the first place. So you have two protons collide, and you use that, what I tell my students, the second most famous equation in the world, E equals MC squared. I usually think of 1 + 1 = 2 probably being a little bit more known. But E equals MC squared tells us that we can take energy and convert it into mass. And in these collisions, we see evidence of that. We'll take the energy of the two protons that are coming at each other and colliding and convert that into new particles that weren't there before. And that's one of the really exciting things that we're studying at the LHC.
Can you accelerate, small nuclei or small ions? Because they still have charge?
Yes, you can. And in fact, part of the time the LHC runs as an ion collider. And so we use lead. And so we'll do lead-lead collisions sometimes, or proton-lead collisions. This is to study a little bit different effect. It's to study something called the quark-gluon plasma is one of the main goals of this running of the accelerator. And that's when you create a volume of space that is just, rather than saying, okay, here's a proton and a neutron and things that go into a normal nucleus, where it's just sort of a soup of quarks and gluons. And that starts to resemble what the early universe looked like when it was much smaller and much denser and much hotter in temperature. So we're trying to study some of those effects in doing that.
Anything interesting happen when you accelerate, lead? Have you ever tried to smash lead into lead, or see if a chemical reaction can actually happen if at relativistic speeds? We're not letting them interact quick enough for a chemical reaction to take effect. They have too much energy for them. We've made them highly ionized and stripped off most of the electrons. So we're looking at the nuclei actually interacting there. So it's a little bit more smaller of a reaction and take very quick time. Oh, so you've been able to ionize lead, rip off all its electrons? So you just have a naked nucleus?
That I don't remember. I'm not that involved in the ion program part of it. My experiment does do it. So the accelerator runs, we generally run 8 or 9 months a year, and about one of those months is spent doing the ion collisions. And a part of our collaboration has a particular interest in that. That's not an area that I work in that much, so I haven't paid that much attention to it.
I guess one more question about it. We'll return to the protons. What's been noticed when you're able to see, I guess, because they're bonded or part of the nucleus, now you can accelerate neutrons, I guess, right? So what happens to them? Anything interesting when they are part of a collision?
So yeah, there are neutrons involved there, and from our aspect, it's sort of like they're just part of the nucleus there. What we're trying to do is get those two nuclei really close together and an overlap at such an energy and temperature that it stops even thinking of it in terms of protons and neutrons being in a certain region of space, but they're just being quarks and gluons, the pieces that are normally inside the proton or neutron. But they're free and moving around and not bound into a proton or neutron specifically. So we're trying to create an area of the collision of these two to create this quark-gluon plasma. There's another accelerator here in the U.S. at Brookhaven National Lab on Long Island that also studies these heavy ion collisions. It uses gold instead of lead, and it does similar studies. They're both slightly studying it in a complementary way. They're not exactly the same, so we've actually started to learn a bit about this quark-gluon plasma and get to understand the force that holds the protons and neutrons together in the nucleus, and even the quarks and gluons inside the protons and neutrons in a different way than we in a different region of space than we had before.
Yeah, I thought that, I guess when you look at, there's the wave-particle duality. So, I mean, when particles are accelerated really, really fast, protons, et cetera, do they have more wave-like properties or more particle-like properties?
It usually has both. We're tending to treat them in the particle-like properties involved there, and less in the wave. We're not looking so much at you get interference effects through the wave behavior there, and I can't say that we don't ever see that, but it's less of a thing, at least in the work that I do.
Yeah. So specifically, what are you evaluating? You smash together the protons. I guess you observe in like a cloud chamber the tracks of various particles somehow. Like how does it work, and what are you able to observe, and what's the consequence of it?
Okay, so we use a detector called the CMS detector. It stands for Compact Muon Solenoid detector. And we're not using a cloud chamber. We've gone a little more sophisticated in order to handle the rate of collisions that we have going on in our experiment. So the CMS detector, we call it compact, but it's about 5 stories tall, and it weighs about 12,000 tons. So that's our definition of compact, partially because the Atlas detector that's also at the LHC is about 50% bigger and about 2/3 of the mass. So it's bigger and less massive. So that's why we think of it as compact. But it's actually a series of detectors that are built in sort of layers around the point at which these protons collide. And what we're studying is then the particles that come out of these collisions. And the detectors are designed to measure properties of them, like their momentum or their energy, the time they take to travel through the detector, where they go, so their directions that they went off, and the type of particle also, which is really important. And from that, we try to take the particles that come out of this collision and reconstruct what happened at the time of the collision. Because usually in these collisions, if we create new particles, most of them will decay effectively instantaneously, timescales such that we have no chance to measure them. They'll decay into some other particles that are longer lived and ones we know well, and those are what will come flying out. But by looking at those parts that are coming out of that collision, we can reconstruct what happened in that very short time frame. And so what a lot of us are doing, the program at the LHC is actually quite wide. So it would take a long time to go through and explain all the different parts of it. So I'll concentrate more on what I and a fair number of our colleagues are doing, and that is the search for new physics. So we have what we call the standard model of particle physics, which is our current understanding of how the universe works. We're studying the smallest pieces of nature and the way they interact. And so we have 17 known particles that fall into that standard model and 3 forces that are included. We don't have gravity included in that model at this time. But so we have this model and these particles, and it does a fabulous job of explaining most of what we see in the world. But there are some questions that it doesn't answer. And so we are trying to find answers to that. We have theorists who are coming up with new ideas to explain it. And we have experimentalists who are looking for evidence of these new ideas or something new that isn't explained by these models. An example of one of these questions you're probably familiar with, and your audience is probably familiar with, something called dark matter. So Dark
I've
matter.
heard about it, that most of the mass that would constitute the universe can't be observed. And go ahead.
Correct. Yeah. So from astronomy and astrophysics, we have the idea that there is much more matter, about 5 times as much matter as we observe in the universe is actually out there. And we don't currently know what that is. And so one of the popular ideas for explaining that is that there is some other particle that doesn't interact like normal matter does. In particular, it doesn't interact electromagnetically, so it doesn't interact with light. So that's why we can't see it. Light will pass through it without noticing it, other than gravitational effects from light. And that's where we do see, one of the places we see dark matter is the bending of light from faraway objects.
Yeah, what's in these? So just like, I guess, like a black hole, you can't directly observe it, but are we able to indirectly observe what we think is dark matter?
Yes. Yeah. So we can see, for example, if you something called gravitational lensing is the idea is that you look at an object that's very far away, and if there's a massive object in between it and you, it's going to bend the light that's coming from that faraway object to you as it goes by that massive object. And that's general relativity. Einstein developed that a little over 100 years ago and was observed through solar eclipses. So if you know how far away that object is that you're seeing, you actually can estimate the mass of the object in the middle. And by looking at that and comparing, so that object might be, for example, a galaxy or a cluster of galaxies. And if you estimate that mass of that galaxy and find out that the mass that you think is there from gravity is much larger than you would count by looking at the stars and the amount of light coming out of it, then you have a measure that there's this extra mass that's involved there. So that's one of the ways that we have evidence for dark matter.
Do we know any of the properties of it? Its density, anything about it?
We do know some things about the density, or we have some ideas at least of the density of it. So we can, through some observations like I was just talking about, you can get some idea of the amount of dark matter in some limited areas. Through modeling of the development of the universe has galaxies clumped together in structure, and from that you can get an idea of what dark matter looks like. By doing simulations of creating the universe, you can get an idea of what dark matter looks like on a larger scale from that. On its properties, we just know that, one, it has to have mass. It can't interact electromagnetically, so through light. It probably doesn't interact with the strong force, the nuclear force that holds the protons and neutrons together there. So that's why one of the explanations that brings overlap from that astronomy aspect of dark matter to my field is what we call WIMPs are a possible explanation for it, weakly interacting massive particles. So
okay, so yeah, what I was just about to ask you. So, what are you hoping to elucidate the existence of WIMPs from these collisions? Is it Large Hadron, or what? Yeah,
we hope to actually produce them in our collisions, and so if they're massive but not too massive, so we can only produce something that is within the energy reach of our accelerator, our collision. And so that gives us a certain range that we can produce at the LHC. If it was too massive of a particle, we could never produce it at the LHC. But there's good reason to believe it probably that there's a fair chance that it isn't outside of that reach. But if we produce it at the LHC, what happens is in that collision, you produce one or more dark matter particles that go flying out of the detector, and we don't detect them at all. And so you might say, well, how are we going to ever see these dark matter particles if we don't detect them in our detector? But we can look at for something called momentum balance. So when we have these collisions of protons hitting protons, we know that if I add up all the momentum of the particles that are flying out of it, and I look at the direction perpendicular to the way they collide, these have head-on collisions, and if I look in that perpendicular direction, there was no momentum initially from there, and if we add up all the momentum afterwards, we should get a sum of zero also. But if these dark matter particles go flying off unobserved, then we wouldn't add that in because we don't see it. And so we would get a measure of these particles, even though we never see them. We can see evidence of them.
So are you confirming that there is dark matter so far with the collisions, or what's been observed?
We have not yet confirmed that there is evidence of the dark matter. It's one of the things that we hope to search for, but we have not seen evidence of it. So if we're producing it, we've either been producing it at too small of a rate to observe it, or we just haven't figured out how to look for it in a way that we would see it. It is a challenge. So another type of particle that we have trouble observing in our detectors is a neutrino, which is another elusive particle. Just so far, the evidence is they're not massive enough to explain dark matter, but we have ways to try to look for evidence of these neutrinos and similar to what I just described. And it hasn't led us to evidence for dark matter so far at the LHC, but we've got a long time of running the experiment to go.
Well, I would think one collision it's over, but how many collisions do you have to do, and what does each one show you? Like, it sounds ignorant. I'm not there, but how many collisions do you need to do, and why so many, and why does it take so long?
It takes so long because what we're looking for is fairly rare. If it wasn't, we would have seen it already. So that's sort of an argument that's, sort of self-explanatory. So this gets even more complicated because when we do collide, I've made it sound a little simpler than it actually is. So rather than colliding two protons together, we actually collide a bunch of protons with a bunch of protons. They cross each other. And most of the protons in each bunch, so it's not a continuous beam, it's bunches of protons going around the rings. And most of the protons in each bunch just pass right past each other and never notice each other. The collisions are fairly rare, except we put so many protons in each bunch that we get not just one collision each time we have the bunches cross, but we actually now are getting up to 30 or 40 collisions every time that a bunch crosses, which means they're happening all at the same time as far as our detector goes for the most part. And we have to look through that to figure out what particles came from which collision within that bunch, and to look for the interesting physics that we want to find. And so what we're doing is we run longer. By running longer, you get more collisions. We also increase the number of protons in each bunch. We eventually, in a few years, will be running where there's like 200 collisions occurring at the same time. And then it's really, you're looking through a lot of particles coming out, trying to figure out what happened in one particular collision that's of interest to you. So these add challenges to looking at the data, but it's the chance of creating these new particles is just, it's very small. So that's why you need to look at a lot of them.
So what's been observed so far? Anything new that wasn't known before? Is there a way to ramp up the accelerator so that you can get to the next level, the next more finer structure? Are you close to any breakthroughs?
Close is hard to tell. So what we found at the LHC so far, the big thing was the Higgs boson. We announced that in 2012, on July 4th, 2012, was announcement of a new particle, which we've since confirmed it behaves like the Higgs boson, which was the last of those particles of the standard model that we hadn't observed, that we knew about. And since then, we've been in a region where we have ideas of what might be there, but there's nothing within our standard model that we think has to be there in order for it to be true. So our theorists are developing new theories all the time that tell us, well, maybe this type of new particle is there, or maybe this type is there, or maybe this type is there. And as an experimentalist, one of our jobs is to explore and look for evidence of these things and shoot down some of the theories, or what would be most exciting is discovering evidence of something new that would tell us maybe this theory may be correct, or this group of theories may be correct. And so right now we're in a region that is exciting, but it's also a little nerve-wracking in that we don't have something specific that we're like, okay, we really believe that we're going to observe this coming up in our data. So we're exploring, and that's why our experiment and the Atlas experiment are very wide-ranging experiments. The programs that we look at are very broad, so that we have the best chance of finding something new, and a little less focused than it was when the Higgs search was going on, or before that I worked at the Tevatron outside of Chicago at Fermilab, where the top quark was discovered. And these were things where you could focus, you knew what should be happening if you can find the particles, you knew how they should be decaying, what they should produce in the end. Now we're in a region where some theories say we might find it in one type of reaction, and other theories might say it's a completely different thing going on. And so you're a little less directed in where to look for. And in my research, I tend to try to look for things that other people aren't necessarily already looking for, exploring new areas and new directions.
Well, what happens when you find, the Higgs boson, or you find, these other particles? I mean, how do you figure out their properties, and then what do you do? How does that help you to improve the model?
So that's one of the big challenges after you find it, is figuring out its properties. So, for example, when the Higgs boson was announced, we were very careful in what we said to not say that we found the Higgs boson, that we found a new particle, and that the next step was then testing the properties of it. So the standard model of particle physics tells us how a Higgs boson should decay, what types of particles it should decay into. So we set up a program to look in those, we already had a program to look in those areas, and some of them we were able to observe it immediately or at the time of the discovery, and some of them we weren't sensitive enough yet to them, and we had to wait for additional data to come in to say, okay, well, we're seeing it in this other way it can decay that we couldn't before, and that helps confirm that it is what we thought it was. And then you have to measure other properties like the spin of the particle. It's like that. When you find evidence of something you don't know what it should be, then it's even more challenging sometimes to measure those properties. And if we find dark matter, it'll be even harder to measure the properties of it, because we're not observing either the particle itself or the things it's decaying into, because it's not decaying there. So that'll be an even bigger challenge. The main thing would be to find something that doesn't agree with what we already know. That's that to me is the thing that changes our perspective and points us in a direction to figure out then what the explanation is. I think that would be very exciting times. We had a few years ago, there was evidence for something new seen by two of our experiments. It was not discovery level, but we presented, both CMS and Atlas presented some evidence for these, and immediately new papers started coming out from theorists saying, here's how you can explain what you see. Here's how, and someone else had a different idea. And there were hundreds or maybe even thousands of papers that came out trying to explain this. It turns out when we looked at more data, the effect decreased and eventually went away. So it wasn't a discovery of something new, but it was that's I guess the first step after you see something new is to make sure that you're really seeing something. In this case, that one went away.
So what's the most current understanding of the structure of a proton? If you're able to visualize it, what does it look like?
So the way I think of it is it's proton is made up of two up quarks and a down quark that are being held together by gluons that are being exchanged. Gluons are the carrier of the strong force that holds those quarks together. But within that, there also is what we call this things called C quarks, and C is SEA, because there's a sort of a sea of these quark-antiquark pairs that are created out of the vacuum or from these gluons that are being exchanged there, and they are being created and then annihilating very quickly. So they live only a very short time period. And this is allowed by the uncertainty principle from quantum mechanics. over a very short time period, you can have your energy uncertainty can be large. So out of nothing, you can create something as long as it only lives a short time period. So the proton is sort of this very busy object with these particles being created out of nothing, these quarks bouncing around, gluons holding it together. And so to some degree, we have a fairly good understanding of that, although there's still a lot of room to learn on that. But a lot of our program is on the new physics and not quite as much about learning more about the structure of the proton.
Okay. Do you still find it's useful for people to think about protons as just a monolithic entity, or do you think that this is going to change, our understanding of physics big time?
I think we have this part understood fairly well. For most people, just thinking of a proton as a proton and a single object is just fine. Those of us who live in the world of particle physics, that's too simplistic of a picture. But for most people, to just say, okay, an atom is made up of a nucleus that has protons and neutrons in it and electrons in shells around the outside, that's going to be as far as you really need to know to go on there. So far, we haven't developed new technology that uses this particular aspect of nature. So it hasn't impacted most people's lives in a specific way. But you just never know where these investigations will lead, and things come out of research, these fundamental questions that were just never expected to be understood and useful.
And I guess last question, can you accelerate or decelerate electrons in the collider? Would there be any use in doing that?
There is use in doing that. The collider is currently not set up to do that. It can be done. So in fact, the tunnel that the LHC is in used to hold an electron-positron collider in it. That had a very successful program running in the 90s and into the early 2000s. One of the challenges there with electrons compared to protons is they're far less massive. And it turns out when you have these lighter particles, when you have any charged particle in a magnetic field and is bending, it radiates off some of its energy. And the faster it's going, the more it's radiating off, more of its energy is radiating off. So bringing an electron up to a high energy gets it going faster and faster, and it radiates off more and more of its energy. And you reach a point where if you're going around a ring, you can only accelerate it so much, and by the time it goes around the ring, it's lost all of that, the energy associated with that acceleration. So you then give it another boost, and it loses that. And so you reach a point where you can't get it going any faster than it already is. And this effect happens for protons, but because they're more massive, it's doing it at a much smaller level. So we're not really bothered by that now. But if we tried to accelerate electrons up to the energies that we have right now, in the ring that is the LHC, we wouldn't get to that high of energy. You need to build a bigger ring, which means tunneling a big tunnel underground, and is very expensive. There are thoughts of people who are interested in doing that, but we don't currently have such a machine there. There's also a program possibly to take a smaller ring, a smaller electron accelerator, accelerate protons only one way around the LHC, and in the smaller ring that's built next to the LHC have electrons and bring them together and collide electrons and protons together. And that's actually an even better way to study the structure of the proton than colliding two protons together. It's a little cleaner there. So there is a program to consider doing that in the future, but that's looking at the end of the LHC's current program is going to run into the mid-2030s, so another 15 years or so, maybe longer than that. But after that, figure out what will go. So yeah, we haven't seen anything at the LHC since the Higgs boson, but we've only taken about 3% of the data we expect to get by the time we're done. So that, the fact that we haven't seen anything is disappointing, but it doesn't mean we're done. We've got a lot more looking to go.
Because of the geometry of the LHC, I wonder if you could extend it a little bit? Instead of 17 miles in the biggest ring, could you add on another ring, or add on to the project without digging a whole new one? And at what size do you think we would really make a breakthrough in terms of understanding?
That one's very hard to predict on what size it would. Most of our predictions said we would have found some new physics beyond what we've seen already at the LHC. There were a lot of predictions that said that within the reach of the LHC, easy reach of the LHC, there was some new physics. We didn't find that. So a lot of us thought we'd turn on the LHC, new physics would jump up and slap us in the face. That didn't happen. So there's often the thought then that, well, you hope that new physics is just around the corner. But it's much harder right now to justify and say, well, okay, if we just go just the next step, we're going to guarantee we're going to find something new. So on the size of the accelerator, the current accelerator was built so that it fit in the space between Lake Geneva and the Jura Mountains in this region of Swiss. It actually crosses the Swiss-French border, the LHC, in running. And so it was designed to fit sort of in this space that was easy to dig a tunnel in. CERN is investigating plans to build a bigger accelerator where they would dig a new tunnel, and this one would potentially both go under the lake and under the mountains, which makes the construction of the tunnel more challenging. It would probably be harder to build a much more powerful. There is talk to try to you can make the LHC more powerful if you had stronger magnets to bend them. So in order to go around the ring, you use superconducting electromagnets to bend the particles. And if you had ones that produced a higher field than our current ones, you could get the particles going at a higher energy, at higher velocity there. So there is some plans to do that, but there's a limit to how much you'll be able to gain there. So there's a lot of different things that are being looked at for electron and positrons, or just electron collisions. They're also talking, there's some folks who are working on plans to do what is called a linear collider, where rather than taking it around a ring, you just accelerate them in a straight line and bring two beams in collision to each other. It has the advantage that you don't have that radiation that causes you to lose energy, but you just you make a more powerful accelerator by building more and more pieces to accelerate, and you can't reuse them. A single beam doesn't go through it multiple times like it does in a ring. That's the beauty of the ring. So when you can't do something with a certain technique, you go and find a different technique where you can do it. It just doesn't mean it has to be easy to do it that way.
Yeah, there's always trade-offs. So.
Yeah, but there's some significant work and talk about building a linear accelerator in Japan, for example. They are looking at, there's proposals to do that there.
Well, very good. Todd, what's the best way for people to follow up and to see more of what you're doing and what CERN is doing?
So I've got web pages. I'm actually in the process of revamping my web pages, make them look a little nicer. But if you just Google Todd Adams and physics, you'll come up with me. Or from there, you can see my email and send email to reach me. It's tadams@hep.fsu.edu is my email address. Well,
very good, Todd. Very interesting. Very complicated, but very interesting. And thank you for coming on the podcast.
All right. Well, I enjoyed chatting with you, Richard. See.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.